Let me see whether I can handle it. Oh no, that must.
We'll go from the opposite. Did you want to?
It's likely that they actually, yeah, maybe that it was for the other side. No. Someone left him.
Let's get started. Good morning, everybody. Welcome to the second day. Just a quick announcement. So the Kaylee for tonight's unfortunately completely booked out already, and there will be an email for another Kaylee on Thursday night. So if you're really interested in dancing, then Elizabeth is insisting that we go to a Kaylee on Thursday.
I'm not insisting, but I am feeling it's very good.
So there will be an email coming out today.
Experience I've ever had. Then.
Absolutely, it is a very nice experience. If you are, so the other two things are we'll have the poster presentation in the second half of today's lunch. So at lunch break at 12:15 as usual at 1 o'clock. Then give the posters a little bit of attention and the people who present posters and standing next to them. And then we'll have the gong show later today. So if you could please give the young researchers presenting the work a chance to highlight the work, that would be absolutely great. Okay, but without further ado, let's continue with the lecture today. We're very happy to have Urs here, and he'll talk about complete topological quantization of high gauge fields.
Yeah, thank you very much. Thanks a lot for having me here. It's a great place, I must say. Many thanks to Christian and the other organizers for making this happen. I appreciate it. So we'll have to go through two sessions today by magic of the rescheduling. I hope that works for all of us, for me and for you. Let's see. But I'll start today with part one. So there are 3 parts roughly, which of course doesn't fit 2 lectures, but let's see. So I'm going to give a Blackboard talk, as you're seeing, which means I'm not covering much ground at all. This will be very slow, but maybe the upshot will be that some good ideas will actually be conveyed. I have prepared notes though with more details and pointers to the literature, which you can find at this URL here. Or I think if you just Google my name and or the title mostly of that talk, you'll also find that page. It's an NLab page which has a talk script and it has the expanded script. So without much ado, let me just start and then we'll see where we're headed. So it's about high gauge fields and about completion and about quantum. So I'll start with things that are very well known, and then gradually we discover that there's something missing, and then I'll explain how to add that missing thing. And at the end, we'll have something that is a little bit more complete maybe than what is usually considered. That's what this word complete is about. So it will be explained in the course of the lecture. So let's start. So we're in Edinburgh, and I gather Maxwell grew up here at least, even though he worked later in London. So it's my pleasure to start with Maxwell's equations. Let's just recall Maxwell's equations as our, for example, of a gauge theory. So we'll be interested in generalizing those in a certain way that I'll describe. And of course, just to bore you, or maybe just to introduce really the kind of notation I'm going to use. So boldface capital letters with the subscript will always mean a differential form on some space-time of that degree. And so we have a Faraday tensor 2 form, which is 0, and we'll do this in vacuum. There's all kinds of variations we can consider, but let's just consider vacuum for a second. In a moment, we'll see some sources appear. And then, of course, the other, so this is 1/2 of Maxwell's equations, and the other half says, so I'll put a 1,3 here to indicate that there's more Hodge star in some 4-dimensional space-time. And so the Hodge star dual of F2 is, of course, also closed. So these are standard Maxwell's equations. And now I'll make a step that is very trivial and yet surprisingly useful. So let's say surprisingly useful. Useful to rewrite this. I hope you can read my handwriting. I'm not actually writing much with my hands, so my handwriting has gotten worse over the years, even than it was. So speak up if it becomes completely unreadable, then remind me to write better. So we can write this as follows. We can say, well, suppose we have F2 equals 0. Now suppose we have another flux density. I'm going to call these forms independent at this point, which is also 0. And then we just declare, oh, but after all, G2 is actually the Hodge star of F2. So these are now 3 equations, and they're trivially equivalent to the previous one. But it's actually, surprisingly, because it may not seem that this is kind of a big deal, but it's actually very useful to write it this way. And from this point of view, writing Maxwell. So this is sometimes called, there's people who are very fond of this, who just care about electromagnetism. They call this the pre-metric formulation of electromagnetism. It actually goes back all the way to Qatar, who was the first actually to write it this way, where you have the freedom to put constitutive relations in the operator. It was later, and this is what I'm going to do next. It's sort of was rediscovered independently in the string theory literature under the name duality symmetric formalism, when we promote these differential forms to higher degree. And that's what I'm going to do now. So I'm just going to declare now. So I want to say, this is kind of a definition or my terminology. I want to say higher Maxwell type. We can debate whether this is the best word for this, but you'll see in a moment what I mean. Maxwell type EUMs. By that I will mean a tuple of fluxes. So here we have two fluxes, 1 and 2, F and G. So I'll write this little arrow here to indicate that we have a tuple. So concretely, I mean we have some index set I, finite index set I, and there is a fluxes F with just an I as an index that just counts them, and they are supposed to. So this is my notation. Omega dr will be my notation for differential forms, smooth differential forms on our spacetime, and they will be of degree I. So each of these fluxes, and we're on some spacetime x1, d. D is the spatial dimension I and I. So on such flux tuples of flux densities, generalizing this pair here, we say higher Maxwell type equations are. So very simply, D, I write it immediately in this tuple formulation. So D of F means it's a tuple of equations now for each I and I. We say that D of the corresponding Fi is, and so we say, well, it's a polynomial of a wedge polynomial of the others. I'll show examples in a moment, but you already see here the polynomial is just 0. It says D of F2 is 0, right? So the polynomials are just 0. In general, the D of Fi is the ith polynomial, some great symmetric polynomial of the wedge products of these. So this is the analog of the left-hand side. And then in addition, we ask, let's see, should I put it next to it? Maybe next to it. We ask that similarly star in 1, d dimensions on our spacetime of each item in our tuple is, and now we say, call it mu. This is supposed to remind you of the mu, which is the conductivity of the vacuum that people like to put here when they consider electromagnetism in media. So in this sense, it's the mu of F, so where mu is a linear map from the linear span of these tuples. So this is a polynomial, and it's necessarily graded symmetric, or just the graded symmetric part matters because we regard it as a polynomial in the de Rham algebra. Polynomials in these variables, and this is a linear isomorphism. Linear iso on the linear span of these F, so it maps them. So here the linear isomorphism just says one goes, it's 0, 1, 1, 0, right? One goes to the other goes to 1. So that's my little definition here. I have Maxwell type equations for flux density. So I'm going to eventually promote this. We want to promote these equations of motion, right? The story here goes, as you know, for 80 years after Maxwell wrote this down in 1850, people thought this is the equations of motion of electromagnetism. And then Dirac came along in 1930 and said, no, this is not actually the full field content. There's, first of all, more to the field content. There's a gauge potential. And second, there's a global consistency condition. And that's what we're after. We want to, right, what's now called the Dirac quantization law. And that's what we're after. We want to understand if these are the flux densities for some higher gauge field, what is the global nature of the actual gauge field? What are the gauge potentials and what is the global constraint? What is the actual field content? This is just the flux density. It's just, we will see the rational part.
X1D.
Sorry?
What is X?
X, this is just my space-time. Is that what you're asking? Space-time manifold. Sorry, I should have said this. 1, d means it's a Lorentzian manifold of total dimension 1.
Manifold.
Space-time manifold, yes. So it's a manifold of dimension 1 plus d, together with a Lorentz, equipped with a Lorentzian metric.
It's great.
Right? Okay. The metric, of course, enters here through the star. The star is determined by this beam. So let's see, what do we do best? Is it best I write here or should I switch the boards? What do you think? We'll see. Okay. Maybe I'll switch. So here's examples. No, I don't like this. Maybe we shouldn't. If you don't mind, let me know, right? What's best for you? So here's the examples we're interested in. I should probably hurry up a bit. Anyway, we'll see how far we get. So here's the RR field in in type 2A can be supergravity. It's a very simple form. I'm ignoring the twist for a moment. Go to the lecture notes to see everything in twisted form. So it says, so our tuple is just, as you know, I mean, this is not, of course you know this, but just to see how it fits together. So this is meant to be a bullet. The tuple is a differential form at every second degree, and they're all zero. And the differential is all zero, and the only way possible they are Hodge duals to each other. So we're in 10 dimensions, 1,9 of f2 bullet, or 2k if you wish, is f of 10 minus 2 bullet. So this famously the Ara fields in type 2A. Type 2B is the same, it's 2 bullet plus 1. Then just to amplify, right? So, I mean, here's this famous self-duality condition on the Ara fields is, of course, this condition. Just to amplify that in this formalism, we can very easily speak about self-dual fields, self-dual high gauge fields, because everything is kind of formulated now in a way that is kind of nominally self-dual. And in order to get rid of the self-duality, we actually kind of double the fields, as you saw here, right? We're actually doubling and then imposing a self-duality constraint to get back to the actual field content. But if we just don't double, it's immediately self-dual high gauge field. The self-dual high gauge field will be so we can write it as, where should I put it? So there's a single item in our tuple. The index set is the singleton. So this has degree 2k plus 1. We're in a 4k plus 2 dimensional spacetime. And so this is 0 again, and then it's self-dual. So star we're in 1, 4k plus 1. So this is in total, we're in 4k plus 2 dimensional spacetime. And since the Lorentzian signature, the Hodge star squares to plus 1. So it makes sense to ask that this is itself. Right? So this is an very easy example of the definition. And that's the self-duality, the self-dual field right there. And then comes so this is all, I mean, this is kind of slightly interesting here. It's going self-dual, but it's all still linear. The polynomials are all 0 so far. So let's see some non-trivial polynomials appear. Should I do it here maybe? No, let's do it here. Let's do the what's called the Maxwell. So let's do 5D Maxwell theorem with the Chern-Simons. So Maxwell Chern-Simons field. So in 5D, so it again has our Faraday tensor as 2 form, which is still closed. But now it's Hodge star. So we're going to introduce it's Hodge star. In 5 dimensions though now, 1,4 Hodge star of F2. So that's a 3 form. So we're going to call it F3 maybe, or G3, whatever you want. And this is no longer closed. The Chern-Simons part of this Maxwell Chern-Simons theory makes the equations of motion of F3 be proportional. So there's some conventional factor here. At this point, we're just working rationally. The exact prefactor doesn't matter. It just has to be some non-vanishing prefactor, but it's a good idea actually to put it 1/2 here right away, but it's not so important. And then it's the square of 2. So in the original Maxwell equations, it would be a source term. This is the point where the electric current 4 form would appear. So there's no electric source explicitly. There's a nonlinearity in the flux densities. They source themselves. The equations of motion say that the magnetic flux is actually a source into quadratic order of the electric flux. So this is a nonlinear Bianchi or identity or whatever you want to call it. Gauss law, we'll see in a moment. And that is going to be very interesting. We're going to see that it's this nonlinear, even though we're talking about a billion generalizations of Maxwell theory, this nonlinearity will make the flux quantization laws that are applicable to these theories actually fall outside the realm of ordinary abelian generalized cohomology theory as introduced by Whitehead. This will no longer be represented by a spectrum, the corresponding flux quantization law, but by another space. And this, I'll come to this in a second. And then, so this is of course the gauge sector off. So this happens in minimal. I mean, just for context, maybe this is not too important for what I'm really going to say, but this happens in minimal 5D supergravity. The gauge sector of minimal. And for more general 5D supergravity, it still kind of looks this way, except that many of these F2 species and some matrix contracting them. So then, of course, the thing that really motivated us originally, but these are already very interesting pieces here, is the C field, or the higher Maxwell Chern-Simons field in 11D supergravity so now we're in 11D, and the flux, so it looks exactly structurally like this up to shifts and indices. There's a 4 flux now, G4, traditionally, it doesn't matter, of course, which letter you use, which is closed. And its star, now we're in 11 dimensions, 1,10 of G4. So this has to be a 7 form. So we call it G7. It's usually called G7. And again, this is not actually closed now, but is sourced by the quadratic piece of the magnetic flux. So we end up at 1.5 here, which is actually kind of important. That's what actually comes out of the supergravity equations of motion if you normalize things properly. Right, so this is the C field equations of motion in 11-dimensional supergravity. And our question is, since everybody's talking about that somebody should complete 11-dimensional supergravity in some sense, you've recompleted something. Let's first of all actually think about how to complete the gauge field sector, because this is not the full field content. This cannot be just by simple comparison to the Maxwell theory. It ignores the gauge potentials and the flux quantization law. So we're after understanding what the right completion of this gauge sector of 11-dimensional supergravity could be. Now we have a little proposition here. So this is an exercise if you want, but it's also worked out in our article called flux quantization in phase space. So wait, okay, maybe I should first say, so we want to, let's analyze the solution spaces to equations of motion of this form. I introduce these general equations of motion of this form here. Let's get a better handle. We'll see that the solution space actually has a very rich or very controlled structure. So for this purpose, assume now that space-time is globally hyperbolic. Space-time is globally hyperbolic. Globally hyperbolic. So what I just mean is that we're assuming our space-time manifold that we just talked about, 1, D is a Lorentzian, as a zero remaining manifold is a product. Right, 1, 0, 0,1 here. So this is the time axis with its negative norm square, and then there's a spatial piece xd, and we're saying, so this is our Cauchy surface. Just a word at this point here. This is just what I want to call it, Cauchy surface. That's what it's called in this context anyway. So, and here we can say, let's call it iota. So for every t, maybe this is hard to read, iota t. So iota for embedding. So this just means, right, we take x here to x at time t. Like this, t comma x. So this is an embedding of the Cauchy surface into our globally hyperbolic spacetime as given by the foliation that is implicit in this isomorphism. And so here's my proposition, which maybe I should have, let's put it here. Let's put it here.
Sorry, why is it 0, 1 and not 1, 0?
It's just, maybe you want to call it, 1. Thanks. Very good. Thanks for So, right. So let me put here first the definition. Let's write definition. Let's write log sol. So local solutions, local in time. So what is the solution space at time t? I write it in words. Is the germs, the temporal germs of solutions to the EOMs, the higher Maxwell equations that are on this board, to the EOMs around time t. Around time t. This is meant to be the set of these things. So what it means is we have a solution around a given t, evolving in time back and forth, and it's defined on some open neighborhood in the time axis. And germs means that we identify solutions if we just shrink, we can just arbitrarily shrink the open neighborhood of t in the time axis. So these are local solutions in the sense of differential local solutions of differential equations. It's just to prevent us from running into issues that these solutions may blow up sometime later in the past. That's why I'm writing local solutions. And so here comes finally the proposition. So, okay, let's put it here, proposition. So then we have, of course, a restriction map from local solutions at time t. We can pull back our forms to the Cauchy surface along this embedding here. And what do we get? We get a set which has differential forms that I'm calling B. Right. So here's a flux density F. It now gets pulled back to B. Just a different name, the name of its pullback, and so it's of the same degrees and stuff. And so, but now on just the Cauchy surface. And so since pullback, of course, commutes with differential forms and with wedge product, these B's now will satisfy the analogous equation in themselves, right? So the same polynomials there, but then it stops. So the proposition says this is an isomorphism. So the point is, on the left, we have this kind of equation for the differential forms we find on space-time, whereas here's just the differential equations just on space. And this is, if you think back to Maxwell equations, this is the Gauss law. This is what's usually called the Gauss law constraint for electric and magnetic flux on the Cauchy surface. And its period here, the statement is there's no further Hodge duality constraint here. The things that are related about Hodge duality here become independent here. This is an avatar of the fact that when you go to phase space with electromagnetism, the canonical phase space, then the canonical coordinate is the gauge potential, which I haven't introduced yet, and its canonical momentum is the electric field, which is independent on phase space from the gauge potential. So it's this independence. We're not seeing the gauge potential here, but we're seeing that the electric and the magnetic fluxes become independent. And the way it works is the Hodge star gets absorbed into this isomorphism, if you think about it. This is kind of the initial value data. And now the Hodge star tells you, well, half of this data is actually, if you know Hodge dualize it on space-time, half of the data becomes the time components of the other piece. So the Hodge star determines how this initial value data actually extends if you go the isomorphism backwards over space-time. But here, we're kind of seeing the first signatures of the canonical phase space. There's no further Hodge duality constraint. Well, so this is a little exercise to compute. And now I need to clean the board, I suppose. Or yeah, why not? Let's see, where should I continue? Maybe here? No, let's continue here, right? So now let's see that actually we can further massage our solution space a bit further. We see now that we are kind of left only with what I like to call the cohomological part, right? So the way we decompose the equations of motion was a kind of a purely cohomological piece that just has the round differentials and independent of the metric. This is why people call it the pre-metric formalism, because just this left piece is independent of any choice of metric. And then there was a metric piece, but the metric piece just dropped out now that we went to the Cauchy surface. So that allows us to further look at what this is. And I'm now claiming, and those of you who know L-infinity algebras will not find this surprising, but I'll claim it now and then explain a bit. So we can further, actually, let's put it here, actually, further prop. This is further isomorphic too. So this is the first isomorphism here. And here's the second one. And this is just equivalent to the set of what I call closed or flat differential forms on the Cauchy surface with coefficients in an L-infinity algebra. So this is math frag A. This is, and I call it A, not G, for reasons that become clear in a moment. Math frag A, right? So this is an L-infinity algebra. L-infinity algebra. This is, I call this the characteristic L-infinity algebra of my equations of motion, because it characterizes, by this isomorphism that I'm claiming here, the solution space. And so why does this work? So let's do a very quick reminder on L-infinity algebras. So I'm concerned here for simplicity with connected. So this is just for simplicity, but here comes an important piece. And finite type L-infinity algebra. So our ground field is the real numbers. Everything is over the reals. This is because we're talking about differential forms. And so that has to, we cannot work over, yeah, we work over so it's like this. So let's here write L-infinity arcs, so for the category, but it's not important. And so, you know, the L-infinity algebra is meant to be E. So this is the A, but I'm calling it G now, L4. So this is math frag G. But it's now a graded, and I'll make it an n-graded vector space. So in degree 0 is the ordinary Lie algebra piece, and then there's higher pieces. And then it has a binary bracket operation on this, but it also now being an L infinity algebra has brackets of any degree. This is a unary bracket, this is a trinary bracket, and so on ad infinitum. And there's conditions now on these brackets that are the analog. So there's graded skew symmetric. There's a conditionality, which is the analog, the high analog of the Jacobi identity. Of course, most of you know this. Sorry for boring you with this, but I want to emphasize, of course, the following perspective, which is one we always use. The quick way to encode this high Jacobi identity and the full structure on the L infinity algebra is actually to form the corresponding DGC algebra. This is, if you want to put it in up here, is a functor of categories. And it sends this degree-wise, so graded vector space in finite type means it's degree-wise finite dimensional. Degree-wise of finite dimension. So with that assumption, the theory of L infinity algebra kind of becomes much simpler than it looks. Otherwise, of course, the same. Because then you can form, so I'm going to write like so for Grassmann algebra. So we form G. This is the degree-wise dual, meaning so it's like star, but I'm not inverting degrees. This is literally in each degree just pass through the dual vector space and then form the graded Grassmann algebra of this. So if we have an ordinary Lie algebra here, we just form the Grassmann algebra of an ordinary Lie algebra where now every element is in degree 1. And now, since if there's higher pieces here, we'll see it in examples. It's easiest to see in examples then we have the corresponding degree shifts here. And now we put a differential on this because this is a differential graded commutative algebra. Differential means it's graded commutative of degree 1. And it satisfies the graded Leibniz rule. By that rule, since this is a free graded commutative algebra, the differential is determined by what it does on single generators, so on lambda 1. So I just need to say what is D restricted to single guys, and then it takes values in this full algebra. And here just declare it to be the linear dual of all these brackets and the sum of these. Right, so the Lie bracket goes from 2 copies of G to 1 copies of G. So dually, we go from 1 copy of G dual to 2 copies of G dual. That's precisely the co-binary part of a differential. And so this being a differential graded algebra, it means, of course, that part of the definition is that D squared is 0, and that is the Jacobi identity over here. This is the infinity Jacobi identity on these brackets. So this is the quickest way to know what L infinity algebra is. And so this construction, this Chevalier-Eilenberg algebra construction, as this thing is called here, is a fully faithful functor. So we actually lose nothing. The full theory of L infinity algebra, the finite type, is remember it here. And now maybe I'll do it right. Let's pull this up maybe and clean this board. What do you think? And now we want to say, what are the, remember I promised that our solution space is the space of flat or closed, as I want to call them, L infinity algebra valued forms. So let's just briefly recall what these are. So what I'm writing now is equivalently known, of course, in many other terms, Maurras-Cartan elements or whatever. But the good way for us, for our purposes, to write it is, if you want the definition. So now given an L infinity algebra, then we say omega 1 DRAM on any manifold X with coefficients in an L infinity algebra G closed is, as a set, the set of homomorphisms of DG algebras, or DGC algebras if you insist, but it doesn't matter, DG algebras from the Chevalier-Eilenberg algebra, from this dual incarnation of the L infinity algebra into the DGC, the DRAM DGC algebra. So this is of G into omega bullet, the RAM of X, the ordinary DRAM algebra. Okay, and so from this picture, you can now see that you see here, if you look at this differential, if you choose a basis of G, the differential will be given by saying, well, on each generator, there will be some polynomial because it has to take values in here. D of any generator will be a polynomial of the other generators. So the relation here is exactly of the form determined by a graded symmetric polynomial and a tuple of them, as we have seen for our flux densities. And that proves this isomorphism here. So let's write down these L infinity algebras that correspond to our gauge. Well, actually, time is short, I suppose. Let me do the following. Let me highlight a source of L infinity algebras that is maybe still underappreciated. So here's a class of L infinity algebras called, let's call it example or proposition. of course, a theorem, really a big theorem, which is Sullivan proposition, given. So it's an example of it's a class of L-infinity algebras given a topological space. So this is now the first time that a space enters. We want to bring algebraic topology into the picture. We've reduced our flux densities to a problem in L-infinity algebra, and now we'll see how spaces, actual spaces, come into the picture, not just infinitesimal spaces, which you can think of these L-infinity algebras as being. Given a topological space, this is now A, curly A. It's the avatar of the calligraphy of the math frag A. And I assume it connected. That's just for simplicity of presentation. It's not necessary. Here's a slightly more necessary. So I assume abelian fundamental group. For those of you who know, we just need the space to be nilpotent to apply rational multiple theory. But let's assume for simplicity that the fundamental group is abelian, just for simplicity. Then it's Whitehead bracket L. It's, I should say, it's R. So we are over the real numbers. R Whitehead bracket L infinity algebra is. So I'm going to call it. This is really hard on the board. Math frag L. LA, or loops. LA is supposed to be a graded vector space, and as a graded vector space, it is the homotopy groups of the loop space of A. So A is connected, assumed to be connected, so there's a essentially unique loop space. So this is well defined, and then tensored over. So as these are all abelian groups, by my assumption that also pi 1 is abelian. Anyway, there, yeah, and with R, right? So we take the underlying graded vector space to be the R rationalized homotopy groups. And then in the differential, by which I mean the CE differential, right? And CE differential, it dually determines the brackets. Differential uniquely fixed by, uniquely up to iso, uniquely fixed by, and this is the theorem part, this is Sullivan's big theorem. So we want to ask that the cochain cohomology of the Chevalier-Eilenberg algebra of math frag LA. Right, this is a cochain complex. In particular, it's even a DGC algebra, but if you forget the product, it's a cochain complex. And it has as such, it has a cohomology. And we ask that this is isomorphic to the actual real cohomology of our space, R. So these CE algebras, what I call, this is somewhat revisionistic here, this is called the minimal Sullivan model of this DG algebra is known as the minimal Sullivan model of A. And it exists under this assumption. Oh, I have to say, given the space A has to be of rational finite type. So we have to assume that that H bullet is kind of implicit when I said H bullet A, R, or Q. The dimension of this, the R dimension of H bullet A, R is finite. This finite type big for space. And so, yeah, it's a fun exercise to work through this. And the claim now is, let's use this board. Here's that is maybe, if I'm running out of time already, a good time maybe to stop. Let's see how things work. So let's see what spaces have Whitehead L infinity algebras that characterize the equations of motions that I'm erasing here. This is of course a bit unfortunate. So you remember the equations of motion that stood here, and we're reformulating them now in of spaces. So it turns out, example of proposition, depending on your taste. So for Maxwell theory, electromagnetism, ordinary Maxwell, we have our characteristic algebra is isomorphic. Yeah, let me just claim this. I don't think there's enough time to. So it's the Whitehead L infinity algebra of the classifying space of B1 of U1 of the red. So if you unwind this, what this really means, this L infinity algebra is just a infinity algebra with a single generator with Chevrolet-Eilenberg algebra is a single generator in degree 2, or 2 generators actually, because we're both closed. So dually, it's the line Lie 2 algebra squared. Dually, as an L-infinity algebra, it has a single generator, 2 generators in degree 1, on which all brackets vanish. So it's a slight graded boost of the abelian Lie algebra R. But anyway, that is the characteristic for vacuum Maxwell. And then for
L stand for Lie algebra or L stand
L, this is the Whitehead bracket L-infinity algebra that I just declared in this example. This is the unique blah, 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 such and such. So it's underlying graded spaces, these fundamental groups, these homotopy groups.
yeah, loop space or
Yes, omega is a loop space.
these.
Omega is base loop space. This is assumed to be connected, so you can choose any base point and it will always give the same answer. So Maxwell has the Whitehead L-infinity algebra of BU squared, BU1 squared here. The self-dual field similarly, well, actually, let's maybe not waste time with this. The RR field, self-dual field is similar. It has Bn, you know, some shifted copy of Bnu1. RR field, now it gets interesting. This is something. So in that case, A is actually isomorphic to, well, this is my matrix L here, which is isomorphic to the classifying space of the stable unitary group. Where this is the union, if you want, of n and n of the UNs, called the stable unitary group. So it's not U of H, it's not crucially, it's non-contractible. It's the stable unitary group. And of course, really, you know, if I may, like if I had allowed connected spaces, and it's an exercise to generalize what I said to non-connected spaces, then of course we would have another generator in degree 0, and there would be BU times Z here. This just drops out because of my simplifying assumption that our classifying space is connected. But this is, of course, this is the classifying space of topological K theory, complex K theory in degree 0. And this piece, if you want the piece with the twiddle over it, that is reduced K theory. So we already see here something that you know, in other venues took more ingenuity maybe to recognize. We already see from this simple analysis that something that looks at least rational like K theory does control the RR field. And now,
This one is abelian, the second one is non-abelian. Is that
well, that's true. As a group, this is not abelian. That is true, yes. But
Yeah, are these computations on what basis?
yes, so I've skipped these computations, right? So first of all, you have to determine the L-infinity algebra, read it off from the Bianchi identities of the RR field. So the RR field has Bianchi identities. We saw DFI, F say 2K is 0 for all K, right? And now we're asking for a space whose Sullivan model has similarly generators in every second degree that are all closed. And so first of all, we need a space which has non-torsion homotopy groups in every second degree. And that is the case for, so pi bullet of BU is Z for bullet equals 2K and 0 otherwise, bullet equals 2K plus 1. Right? And then you want to ask what bracket to put on the graded vector space spanned by the realification of these in order to reproduce the cohomology. But the real cohomology of BU is also this form. HBU of R is also, you know, it's R if bullet is 2K and 0 otherwise. So we know that if we just use this set of generating elements with that differential, we have found the Sullivan model. And so you can translate it into the L-infinity algebra. It just means you have an L-infinity algebra that is generated in every odd degree. And again, all brackets are trivial. So the L-infinity algebra is actually pretty trivial. It looks just like a direct sum of shifted R's. But nevertheless, that's what it is.
And a naive question,
Yes.
who is B in this setup?
This means classifying space. So B of a group is the unique space whose base loop group is homotopy equivalent to that group. So if G is a topological, sorry, I assume G a topological group, or more generally an infinity group, like a loop group would also work. G a topological group, then BG is called the classifying space, the Milgram classifying space or something, is characterized by, is a space characterized by, so it's loop space, omega BG. So it's connected. I should say, sorry, this is not very organized. It's the connected space whose loop space is homotopy equivalent to G. So this characterizes the space up to homotopy equivalent. So this is the space. Okay, put that here. Well, I come to this actually next. How much time do we have? 3 minutes? No minute.
No, yeah, probably. 3/4 of now. 10:45, you have 1.5 hours per lecture.
I see. Okay, great.
Can I ask another question then?
Yeah.
Seems that the mass frag A should be determined by like only the initial data, the B's, the mu's, and maybe the index set I.
Yes.
Is that correct?
Yes. No, mass frag A is absolutely of this form. So I should maybe write it down. CE of mass frag A is exactly the free. It's spent on the. It's freely generated by the F's, by the F species, subject to, right? We have to define, this has to be a differential graded algebra free on, whose underlying graded algebra is free. So this is the free graded algebra on F, and then the differential in the Scheibler-Eilenberg algebra is just, so we should let's call them B. The index, they have the same index set, right, and the same degrees as the F's, but they're formal generators of every degree. And so D of the B's, it's always the same formula as P of the B's. This is what characterizes A, because remember, mass frag A was determined by the fact that homming CA into differential forms reproduce our equations of motion. But now as we hom this into differential forms, what do we get? Well, each generator has to go, right, if we map this to differential forms. So each B here, BI, has to go to some differential form. Well, it goes to Fi. It has to go to a flux density of that degree. And then the differential has to commute. So here the differential takes BI to PI of the B's. And then since this is an algebra homomorphism, it respects these polynomials. So this polynomial in the B's goes to corresponding polynomial in the F's. And this has to be, so this is the differential in the Scheibler-Eilenberg algebra, whereas this is the de Rham differential. So you see that having a DG algebra homomorphism like this exactly says that you reproduce our equations of motion. These abstract generators become fluxes, and their differentials have to be preserved. That's how it works.
Is there an obstruction for what you wrote on the right-hand side to be the Scheibler-Eilenberg algebra of something?
Yes, it's exactly this constraint that, is it still somewhere? No, it's not somewhere. Or here. It's that it's semi-free, wow, some people call it. That the underlying algebra, the underlying graded algebra, forgetting the differential, has to be kind of the Grassmann algebra on a graded vector space. So it has to be a free graded commutative algebra. And then that is exactly the essential image of this functor. For every, you can turn this around. If you just start with a graded commutative algebra here and put a differential on it, then, well, the differential will have a co-unary part, a co-binary part. So by dualizing, it gives you all these brackets on the vector space that generates this free algebra. And again, this equation tells you that's the same equation. Yeah. Right. So what I'm saying here, this proposition is a sort of an easy exercise, which maybe I should have spent more time on this. I thought I had less time.
Just another, well, why is it useful to get these from a space instead of just?
We'll see this in a moment. Exactly. We'll see this in a moment because we are after completing our field content. So next we want to ask, this is exactly the next step. We want to ask, what about flux quantization laws? Can flux densities actually in reality take all possible values, or is there a global constraint? And that global constraint will be exactly encoded by that space. So that's why it's useful to have this formulation.
There is no t dependence in the moment. Time dependent.
Very good. Let's come. Okay, these questions all point to the next thing. Up to isomorphism, not, but that's exactly the next point. So we chose a Cauchy surface, and on a Cauchy surface, we got particular flux densities. Now we should ask, what is the total flux in the system, right? So remember back the case of ordinary Maxwell theory in Dirac's original argument. You have magnetic flux F2 on the complement of a magnetic monopole. So in a spacetime that looks of the form, it's this two-sphere around a monopole times something contractible. Then, okay, now you have some two form on the two-sphere. You want to say the two form is a flux density. It tells you how much magnetic flux goes through this two-sphere. The monopole is sitting here. We imagine in Faraday's old picture, right, that there's flux lines going through, and the two form tells us how much flux per unit. But of course, the charge of the monopole is the totality of the flux as kind of the integral over, well, in the Maxwell theory, we can actually integrate our form over the surface and call that the total flux. And after some flux quantization supposed, which we'll get to, the total flux will be some integer multiple unit charge. So now that we're talking about these non-abelian forms, we need a bit more clever about what we mean by total flux, because just the plain integral doesn't make sense. And then we observe the following. So we observe that so total flux should be that. Right, what is total flux? Well, one characteristic property of total flux is that it's meant to be preserved on a time evolution. It's not in our globally hyperbolic space-time, it's meant to be the same. So we can just declare total flux is the time invariant, let's say, invariant or flux densities. So let's just formalize this, or flux densities. So let's just, I'll try a picture in my notes. I have a picture, so, but I'm not sure if I can do this on the board. So here's XD, here's the time axis. And say here's T, or let's say here's T, and we have a Cauchy surface. Should I try my luck? So here's a Cauchy surface, but here T prime is another Cauchy surface. And now maybe I should have drawn it like so. And now things are evolving. So here's some densities, some flux densities evolve. This is I'm not sure if this makes sense. Anyway, this is the evolution of our system. And we know at each Cauchy surface, so here, the flux densities are given by a map to the Ram algebra of this copy of XD at T. So we have a homomorphism from A. So this is our forms B, our magnetic forms at time T. It's a homomorphism of this form, right? Closed form. This is the field content, the on-shell field content on this Cauchy surface by what we just saw. And now I should have drawn these more apart. At time T prime, we have correspondingly the solutions here. So this is another copy of XD at time T prime. There's a homomorphism here. So this is the flux densities, electric magnetic flux densities at time T prime. But now, of course, since in the space-time cylinder in between, these things still satisfy these same differential equations, d vec f is p of f. We actually also have in here differential forms on 1 plus d on the cylinder. Let's write it as the cylinder. The cylinder t comma t prime. Sorry, this becomes hard to read. I should have used more space. Sorry for that. Maybe you can see what I mean. So here's the differential forms on this cylinder, right? And it has restriction maps to there and to there. This is the restriction maps. And we have a map here. This is our actual f. Right? Remember, this was the definition of B's. The B's, if we had an f, which was a homomorphism like so, the B's were the restriction to the Cauchy surface. So we have this commuting diagram. And now we see from this is called the concordance. This is called the concordance of differential of flat L infinity algebra valued forms. Namely, you have flat L infinity algebra valued forms on XD and another set on the same XD. And the concordance is extending them to flat differential forms on a cylinder over XD, which on the boundaries restricts to the given. It's like a homotopy in the context of these forms, concordant.
But the underlying space is not changing, only the metric from T to D prime. Or could it also change?
No, by my assumption, I assumed this globally hyperbolic space-time, so it does not, otherwise it wouldn't, no, because otherwise we don't expect the charge to be conserved, right? The space is sort of the same XD here, up to diffeomorphism. Yes. So we now declare that, so you see, this is, we can now, concordance generates an equivalence relation. We can quotient out by this, and that is certainly a time invariant now by construction, because it quotients out time evolution. It says two of these flat differential forms are regarded as equivalent if one actually can be obtained by under time evolution from the other. So we declare now the non-abelian A-valued value, the RAM cohomology of the space X, XD in our case to be, so I'd write it H1, the RAM. The 1 is always because all other degrees are kind of encoded in A. So in X, coefficients in A, declare it to be simply the concordance classes of the flat forms, which were denoted like so. Mathfrag A, closed modulo concordance. These things that I'm saying now, they're all in this book. This is all described in great detail in our book, the character map. This is section 6 of the character map in non-abelian cohomology, which is the thing that comes next. So why do I call this the RAM cohomology? Well, for that purpose, it should be the case that if A here is of the form Whitehead L infinity of B and Z, so if it's an abelian L infinity algebra that is just considering a single degree and all brackets vanish, then this just becomes ordinary closed forms. And concordance, one can check, it's an easy exercise, is equivalent to there being co-boundaries. So in that case, this reduces to ordinary de Rham cohomology. This is another way to do this. It's kind of, back in the days, I call this integration without integration. It picks up the integral of the form without actually performing an integral.
Are there easy, interesting examples where you actually have higher Lie brackets?
Yeah, so the two examples, my two running examples are for the 5T sugar and 11D sugar case. Maybe we lost sight of that. So for the let's take the 11D sugar case. So the Whitehead L infinity algebra of S4
Okay, yeah.
has generators. So it's as a linear space. It's generated by elements, one element in degree 3. There's always this degree shift when you pass from L infinity to 7. So this corresponds to G4. There's a guy V6, which corresponds to G7. And the non-trivial bracket is the only non-trivial bracket is V3. V3, comma V3. Right. This is an odd guy, so this does not have to vanish. This is graded skew symmetric, and that is into the conventions either 1/2 before. Then actually there's 1 here, so this is to V6. This is known, so this is still a very simple case of an L infinity algebra, but it has a non-trivial higher bracket. This is known in the literature. This was, without understanding it as being related to the force sphere, this is known in the M-theory literature as the M-theory gauge algebra, or the 11D supergravity gauge algebra. That's how people call it, gauge algebra. And that is the characteristic algebra really of. So you see, there's even trivial unary bracket, but anyways. Let's see, what else did I want to say? And similarly for S2, right? So it's just by degree shift. LS2 is R of V1, comma 2. And the non-trivial bracket is 1, comma V1 is V2. All right, I should say at this point. So you see the examples of L infinity algebras that appear are comparatively simple. Right? There's no huge infinite dimensional space and loads of brackets. It's a few brackets. And it has to do with the fact that we're using L infinity algebras. I should highlight this in a rather different way than you're maybe being used to, right? So so there's two roles of L-infinity algebras, and I'm talking about an unusual currently role, an underappreciated role of L-infinity algebras. So mostly in the higher gauge literature, that's not what I'm doing. They appear as coefficients of gauge potentials, right? So you all used to probably, or those who've looked into higher gauge theory, consider maybe principal higher bundles whose connection forms take values in an L-infinity algebra. That's not what we're doing here. In that context, the flatness condition we're talking about is a non-generic condition, which in general you don't want, right? Which is not the generic constraint. Whereas here, it's as coefficients, it's a shift in perspective of the flux densities. So these are very different breed of L-infinity algebras in a way. So here the flatness constraint is not only generic, it actually encodes the equations of motion, the Bianchi identities. So flatness here is non-generic, generic. Here flatness is drives the theory, is the Bianchi identity, is the EOMs. And we will see when gauge potentials arise, they may not even appear as L-infinity algebra valued forms. You already know it for the usual story of K theory. If you believe the standard K theory quantization of RR fluxes, then the actual gauge field is a co-cycle in differential K theory, and that is not given by an L-infinity algebra valued form. It's at most given by an ordinary Lie algebra valued form on some vector.
Naive question,
Yes.
the restriction given by the Hodge dual in the
Yes.
equations of motion, where is encoded here?
So no, right. So this is really just the cohomological part of the EOMs. This is, I could say, is the Bianchi identities. It's the Gauss laws, Bianchi. So it's everything except the Hodge duality. Bianchi, Gauss. It's the cohomological part of the equations of motion. Okay, so now, right. So now we want to ask. So we know from, where should I continue? We know from reality, let's say, well, this is a starting point, actually, that there is a quantization condition on ordinary magnetic flux. This is what's called Dirac charge quantization. People always in this context talk about magnetic monopoles and how they imply this, but they're not actually there. But if there were somewhere in the universe magnetic monopoles, so it's a bit of a hand-waving thing. What is maybe underappreciated is that Dirac charge quantization also controls what's called the integer number of Abrikosov vortices in type 2 superconductors. And that kind of proves experimentally that some form of flux quantization, charge quantization, or the magnetic field is in effect in nature. And so we're asking now how to encode flux quantization laws. Encode flux quantization laws. So we want to say, okay, not all flux densities that solve the equations of motion may actually be realizable in nature. The total flux they have may have to satisfy some constraint. The total flux we think of as being sourced by some charge, by some monopole or by some brane. And that brane, or monopole, we expect to come in some integer units of some charges. And hence the fluxes it sources must also follow this discrete, in some sort, law. So this quantization is in the naive, at this point, it's in the naive sense of discretization, coming in discrete quanta. Well, let's see. So we have now, so here's the definition proposition. So let's denote, let's introduce some notation. So A as before, let's write LQ. So I'm just throwing this at you know. Some of you may not know this, but I will not really spend much time with it. But let's it's a brief idea. LQA is the rationalization of A. Should I explain this? So this is a topological space, which all whose homotopy groups are rational. They form rational vector spaces, and there's a comparison map eta q from A to LQA, which is an isomorphism on rational homotopy groups, which is universal with that property. So this is the best so LQA, the rationalization of A, is the best approximation of A that retains all the non-torsion information. If there's homotopy groups that contain finite group factors, they all disappear under this comparison map. So LQA is the space that in a sense recovers. So for instance, LQ, let's do a very simple example. LQ of BZ or BNZ of the integral of the classifying space for integral cohomology is BNQ. This is characterized by having a single non-trivial homotopy group in degree n, which is the integers. This has a single homotopy group in degree n being the rationals. The rationals being the rationalization of the integers. Right. So this is a full space, and this is kind of its non-torsion image. And we'll see in a moment by a non-abelian de Rham theorem that this piece is, as you would hope to expect, this piece is recovered by the de Rham cohomology with coefficients in mathfrak LA. This is the torsion, the rational part we've already been considering, whereas this is the piece we want to introduce now, the one that is more constrained. And let's see, what else notation do I need? And then I can already define maybe. Are we? So then the character map, this is definition, proposition, the character map in A cohomology, in omega A cohomology. What is that? I have to say it. I will say it. So this is character map. This will turn out to be a generalization of the Chern character map. If you put in the classifying space of K theory, it will come out as a Chern character map. Put in the classifying space of ordinary cohomology, it comes out as the de Rham homomorphism. So it generalizes this approximation of a cohomology theory by differential forms. And so it goes like so. So on the right here, we want it to take values in our de Rham cohomology, and our non-abelian de Rham cohomology on a manifold with coefficients in LA. And now we want to have like an integral analog of this. We want an actual cohomology theory, like in the sense of not necessarily de Rham, so no de Rham index. And the role of this is like, as we saw, this LA, right? This with the homotopy groups of omega A. This is like an infinitesimal version of the loop group of A. This remembers something about the loop group of A. So let's put the actual loop group of A here. Think of the loop group, as you may, this is an infinity group. Think of it as being the analog of a topological group. In fact, every loop group is homotopy equivalent to some topological group. So you can think of this as being a topological group. And as such, there's the ordinary notion of non-abelian cohomology, which classifies the principal bundles. So structure group is this group. And the way to formalize this is on principles. We can actually define this as being the connected components. So it has like all good cohomology theories, it has a classifying space. They classify the classifying space as A. So consider the mapping space, the space of all continuous maps from X to A, and take its connected components. Is that okay? So this is the set of all continuous maps from X to A, and there's a natural topology called the compact open topology that makes this a topological space. And the connected components of this are the homotopy classes of these maps. So you can think of this as being the space consists of maps F prime, but then when they're homotopic, they get identified in pi 0. So it's this modulo. This is the non-abelian, like if you put here B and Z, for instance, which is a KZN, a classifying space for ordinary cohomology, this becomes ordinary integral cohomology. If you put here the classifying space BU times Z of K theory, this is complex topological K theory. But the thing you put here doesn't have to be a space in a spectrum of spaces. It can be any space connected in my assumptions. So this is non-abelian cohomology. And now we want a comparison map that kind of extracts the differential form data. That forgets the all torsion information here, just remembers the rational piece. Well, it's easy to see now what this should be down here, because we just saw that we have this comparison map of the classifying space to its rationalization. We're just mapping into the classifying space, so we can just post-compose with that. So I should say I didn't introduce this here. I'm going one step further here to L by extension of scalars. You can you can then R rationalize it. So have this the unique space such that all maps become R, R rational homotopy equivalences. So then we map to then this is, so this set here of non-abelian cohomology classes canonically maps to what may be called the rational non-abelian cohomology with coefficients in LR A in this classifying space that forgets the torsion information. And then the theorem that we prove in this book, character map, the non-abelian de Rham theorem, says this is actually isomorphic. So again, in the case that A is actually B and Z, classifying space for integral cohomology, this is the ordinary de Rham isomorphism. It says then this becomes ordinary real cohomology, and it's the usual statement that de Rham cohomology in some degree n is isomorphic to the real cohomology in some degree. So this is the generalization here. So this is a non-abelian de Rham theorem. This is proven by tools from rational homotopy theory. So the way this works, you represent these spaces themselves by Sullivan models using the model category equivalence between rational spaces and these DG algebras and so forth. And then this follows by rather classical facts, but I don't think it has previously been formulated in the way that we need it here before we wrote that book, which was the purpose. So you see, this way we have now defined a map. We say, okay, non-abelian cohomology is maps into a classifying space that can be approximated by maps into the realified classifying space. That is actually the de Rham cohomology with coefficients in an L infinity algebra. So in total, this map now exists as this composite, and we call it the character map. This is the character map. So for example, I would need more water. That's a bit of the dust. So I already mentioned it. Should I write it to the board? So if you plug in, I said it a few times already, right? If you plug in B and A is B and Z, and it becomes the de Rham homomorphism. If you plug in A is BU times Z, it becomes the Chern character on K theory. There's twisted versions of this and differential versions of this. So this is the analog. In fact, if you plug in any spectrum here, this becomes what's called the Dol-Chern character. There's a Dol defined the analog of the Chern character for all abelian cohomology theories, and it also just follows from this perspective. Okay, so now we can talk about flux quantization. So it's sort of the baby version. But this is not yet the full answer. It's kind of flux quantization on isomorphism classes, not yet really the local version. So it's kind of flux quantization 0. I don't know. So it's a form of flux quantization, but it's not yet the full completion of our gauge field content. And now we want to say, so flux quantization is a choice of A. So we have I'm assuming we have our equations of motion, our fixed higher Maxwell equations. So now we choose so that gave us this L infinity algebra, the characteristic L infinity algebra A, which characterized completely our higher flux equation. And now we ask, let's choose an A such that its Whitehead L infinity algebra is that A, which we've already been doing in the examples. I already put some A's there. But you should know that, should be aware that in general, there's many A's that have the same Whitehead L infinity algebra. The Whitehead L infinity algebra forgets a whole lot of information, forgets all the torsion information. So there's this choice, either it may not exist. There's L infinity algebras which are not Whitehead L infinity algebras of any space. But if it exists, there's always an infinite amount of choices. Large, for instance, e.g. if A, so if you have this, if A satisfies this, then also A times BK satisfies it for K a finite group, for K in how should we write it, groups in finite sets, right? Because a finite group in finite set has all torsion homotopy groups, its classifying space. So this is 0 under applying L. You cannot see B's of finite groups. And so this space will just as well be a classifying space. So it's these kind of, there's much more intricate other ways in which you can change A, but this is a very quick way to see that this already gives you an infinite amount of choices. And I think this is important to know because this already applies to just ordinary drug quantization. It's not clear actually that I don't doubt it actually, but it's not mathematically clear that the electromagnetic field is really a connection on the U1 principal bundle. It could be something more fancy. There could be funny stuff going on with torsion, which we just haven't seen yet. Because the only, as I just said, the only probe of this conjecture, of this hypothesis, is really for abrikosov vortices, just evaluated on a two-sphere. So if there's any torsion piece in A that when evaluated on two spheres is not seen, it could be there and we wouldn't know. Also, the K-theory classification of D-brane charge, people just behave as if it's a done deal. Even if you buy into the usual arguments, there's still room to add torsion pieces. Just to say that all of these are hypotheses. Anyway, so let's say, so what we want now, we want to say, so then let's promote our flux densities to pairs. To pairs, a flux density and the chi, which is a charge. Let me write it like so. Maybe it's an actual charge now. So the flux density is defined a total flux, and we want to say that total flux is sourced by a charge, xdA, xc omega. So let's say it's a pair such that they agree, in where they can. So they don't live in the same space, so they can't agree on the nose. So what do we mean? Well, we have now a map from these closed de Rham forms. Oops, D, A. So F lives here. F is a guy in here, closed. And now we just saw that this actually maps into the de Rham cohomology, into the non-abelian de Rham cohomology on XD. By taking its total flux, its class. But we've seen also that that there's something else that maps to the de Rham cohomology, namely the full cohomology, the non-abelian cohomology, XD. A. So chi lives here, the class in here. And now we've seen F maps over here, forming total flux. And it gives the class in cohomology, which is the total flux, but also chi maps over there by the character map that we just constructed. And it gives the character of chi. And so we can ask these to be equal. And that is the flux quantization condition to zeroth order. So this says those go right. So if we say we have pairs such that they fit into this diagram, the condition is now only those flux densities are admissible whose total flux is the image of the character of a charge, which is sourced. The total flux has to be such that it looks like it has been sourced by an actual charge. But what exactly charge means is a choice or hypothesis. It's an extra ingredient that you need to specify in order to complete your theory. This is an important point I want to maybe highlight. We discover here that we haven't, in writing the equations of motion, we haven't actually looked at the full physical model yet. There's something to be determined. What is the full physical model? And it's a further choice. And with that choice, you have a physical model and you know what the charges are.
Sorry, this is a bit of an ignorant question, but on that concordance diagram there, we are still saying that F is like in B higher forms, but then
Oh, yeah,
here we only have like one forms. Is
No.
alpha that is
No. Sorry, this is minus. These are one forms with coefficients in the, so they are higher forms.
okay, yeah, that's
Sorry, this is a, yeah, I do write it this way. I know that it's sometimes confusing, but it's actually important to write it this way. This is the right way. This is one forms with coefficients. Here for ordinary Lie algebra, you have one forms with coefficients in degree 0. It's just the one form. But now this is a 2 algebra. It has something in degree higher degree than a one form with coefficients, and that is actually a higher form.
yeah, okay.
I write one there. It's kind of this one is the shift that keeps happening here. It's the shift between A and omega A, because you can see it here very clearly. H1 with coefficient omega A is actually, I just said, you can ignore this. I just said because you asked. This is H0 with coefficients in A, because this is the delooping of omega A. And if A itself were actually B of something, you could go to H2.
Yeah,
H2. So ignore this for others. Yeah. All right. Yeah. Thanks for asking this. We're not talking about just one forms. So
How does it work with, how does it fit with the naive picture that you get the charge from integrating the fluxes?
Yeah, so in the ordinary, exactly. So if we choose the ordinary, let's remove this here maybe now. I don't know, I forget what should I do? Maybe this? Right, if we now choose, let's go through the examples. Let's do ordinary Dirac charge quantization. So I'm actually choosing now the spaces that I've already indicated as being my canonical choices. You can try other things, but there's now an evident choice actually in this, how should one say, so the choice of flux, even though the choice of flux quantization laws A is large, there's kind of some things are smaller in there. So if we, for instance, think of A as being represented by a CW complex, then you can ask for CW complexes having very few cells. The simplest choice for the ordinary case gets us back into the ordinary situation. So let's call these hypotheses. Hypothesis. How does I hypothesis? I don't even know. Hypothesis for flux quantization. In the sense of, remember what I mean by this. It's hypothesis if we speak about doing actual real physics. If we think the physics is fixed, like if we think the electromagnetic field clearly exists, now we want to understand what is its flux quantization, or we hypothesize what it is, right? We make a model. Or if we believe, which is a big if, of course, that M theory exists, it's just, we just have to find it. It's not a matter of us choosing something. Then, okay, we have to make a hypothesis about what its flux quantization law is. It's in this sense. So the first one here just goes by the name Dirac charge quantization, even though it is a hypothesis, and as I try to, like, it's not clear that it's a done deal yet. But anyway, it's called Dirac charge quantization. And remember, we had A, I already wrote it in the suggestive form, so this will make things look a bit trivial now. I already noticed that the L infinity algebra is that of BU1 squared. So then we can just choose, let's choose A to be the actual BU1 squared. But this is admissible because L of it is A, right? But I'm just to amplify, this is just one choice. You could go and add BK for K in abelian, for K a finite group, or a finite infinity group or something. So it's a choice, but it's kind of verified by, I mean, there's the square here, right? Also notice this has been only considered more widely in recent years, or Dirac wouldn't have had a square here. He only quantized the magnetic flux, not the electric flux. People later noticed that, well, why not? Why would the electric flux not be quantized? For our picture, where we're on phase space and considering non-abelian Bianchi identities that mix electric magnetic fluxes, there's no way that we could flux quantize just one of the two. What you could do is, if you don't want to quantize the electric flux, you could say, no, let's take it to be BU1 times B2Q. So this for the magnetic sector, the usual theory, and this is kind of essentially no condition. It's just the rational space itself for the electric sector. So this would impose essentially no condition on the electric flux. It's another choice, actually. Anyway, so this is Dirac charge quantization, and then there's something. So then there's something I like to call now hypothesis K. Just this is not how it's usually called, of course, but I do want to call it this way because to amplify that this is not actually set in stone. So for the RR field, so this was for the M field, and so for the RR field, this is of course the famous hypothesis that people have written many articles about. We know that the RR field has characteristic L infinity algebra being the weighted L infinity algebra of U. So let's take A to be BU or BU times C if you generalize my board account to unconnected spaces. So this is KU0 then, the classifying space for K theory, and its hypothesis says the total charge of RR flux has to be a class in K theory. Hypothesis K. And in this vein, we now continue, and then it's kind of obvious what I'm going to say next. So next we call this hypothesis H with a little h, lowercase h for the 5D Maxwell field, Maxwell CS 5D field. Remember, again, it's kind of the most obvious choice that you can have. It's not meant to be, it's not necessarily the right choice for whatever you want to do, but it's the first one you want to look at, because we saw that well, or I claimed, I didn't really, there's time I can explain how this works. I claimed that, remember these equations of motions, df2 equals 0, d3 equals f2 wedge f2 is classified by the weighted L-infinity algebra of the two-sphere. And so the evident choice, and it's actually the minimal choice as far as CW cells goes, is to take A to be the two-sphere. And the two-sphere classifies what is called cohomotopy theory. So the corresponding non-abelian cohomology, X omega S2, is actually known as, this is known as pi2 with an upper superscript 2. This is cohomotopy theory. In the same way, this is actually co-K theory, right? This is K cohomology. So whether this is K, this is H for homotopy. That's why it's called hypothesis H. And it's lowercase because this is a 5D version. And you can already guess now the 11D version is then hypothesis. This is H. So C field in 11D. And the hypothesis says that, well, given that it's characteristic L-infinity algebra is the weighted L-infinity algebra of S4, well, what if its classifying space is actually the fourth sphere? Well, this would be 4 cohomotopy, right? So now non-abelian cohomology with coefficients in omega S4 is called pi 4, superscript 4 of X, 4 cohomotopy. So these would be flux quantization laws for how to impose flux quantization on high gauge fields. And now, I guess now, if I'm counting right, I have a few more minutes, right? So let's just, as an outlook, and we need this for next time, let me give you a hint at least. This would require a full lecture to fully explain how to now actually construct a full phase space. So why is that not enough? What here's the board. Why? So we said, okay, there's flux densities and there's charges like that of a monopole or something, which force these flux densities. And then there's this equality. And now we're talking high gauge theories. And the moment I write an equality, you should, some alarm bells should go off. You should say, no, this is not what you should do. You're missing some structure. We want to promote this, of course, to a homotopy, so to a gauge transformation. We don't want to say that the class of F equals the class of chi. We want to say that F is in some way homotopic to chi itself, such that then, if you pass to pi 0, it reproduces this equation. So we're not losing this equation. That's why it's step 0. So it's not wrong. This is part of it. But to get the actual gauge field content, we make this a homotopy. And it's this choice of homotopy by a little miracle of math that actually encodes the gauge potentials. We haven't seen the gauge potentials yet. The gauge potentials are, as a slogan, the homotopy that relates the flux densities to the charges. So to formalize this, one needs, where should I go? Here maybe? One needs, geometric homotopy theory, the topos theory. We need to find a context in which differential forms live in the same world as homotopy types. And that is the context of smooth infinity groupoids, of the infinity topos over a smooth manifold and stuff. And there we can say the following, and I'll just indicate it. So maybe before I write any diagram, so in the full theory, finally, the actual completion, actual flux, the actual completion, global completion, of our gauge fluxes, or high gauge fluxes, with a choice, with choice of flux quantization law. Is so still somewhat schematically is so the full phase space, the full on-shell field configurations. So these are the full globally complete on-shell. That's what makes it a phase space, on-shelled gauge field configurations. Are, so this is in quotation marks. I write a triple here. So are the, oh, here's a typo in my notes. Okay, are the flux densities, triples consisting of the flux densities F charges, or local charges, let's call them. So I haven't taken the class yet. Local charges chi. My arm is getting weak. And then gauge potentials. I'm going to put it A hat. So locally, these are going to be the forms that you know, the gauge potential forms. They're globally defined now, and they're kind of a homotopy from chi. So how is that? So this should really be quotation marks. So how is that really? But this is the idea. The phase space will consist of these triples. Namely, the phase space will be a homotopy pullback of smooth stacks between a sheaf of differential forms, space, the classifying space of the charges, and it will be filled by homotopy over a space where they coincide. Let me very quickly indicate this, and then I'll stop. I'll just write some symbols now, which I don't really have the time to explain. So here's what I actually mean. So there's a smooth set, and I should say Gregory will talk about this in the Gong show later. This is the point where our talks finally connect. Whereas Topological is working with us in NYUAD on related matters of using higher topos theory and topos theory for describing physics, and maybe he will say a bit more in the 5 minutes here. Probably not. Anyway, so there's something called, this is supposed to be a boldface omega. It's a smooth set, meaning it's a set, but it has smooth structure. These are our flat forms here. And with Hisham Sadi, they wrote a very nice article, Smooth Sets of Field Histories, or of Fields, which explains how smooth sets on the form I'm not explaining here are useful in doing ordinary classical field theory. And so this is the smooth version of the set of solutions that we had before. This is our solution space promoted to a smooth space. And it turns out it maps to something. This is not an integral sign, but it looks like one, which is maybe a better idea. This is the shape. So should think of it as being, it's the path infinity groupoid construction, path infinity groupoid construction. And it's a long story why it's denoted this way. So this is the space, turns out, where things are comparable. So this is this moduli stack, it turns out, of the formations of these. In here, zero truncated stack. Every form just exists as a form. It's either equal to itself or not. I mean, it's not equal to anything else. Whereas here, there's morphisms. This is a higher groupoid, where morphisms are concordances, and higher morphisms are higher concordances. So here things can deform into each other. And then here is our space of co-cycles in non-abelian de Rham cohomology A. And then there's a version of the character map, boldface character, that sends this to there, so that approximates the local charges by kind of deformation classes of forms. And we're forming this homotopy pullback. And this is our phase space. So this is, for our purposes, the phase space, and it's filled by a homotopy, being a homotopy pullback. And that homotopy pullback is the A. So this homotopy here happens here. It's really a homotopy between the character image of chi and this thing, eta shape. And in a different language, this is also the differential A cohomology of. So another way of writing this here, this is H1 differential cohomology of XD, coefficients in omega A, canonical differential A cohomology. This is a version of the Hopkins-Singer pullback diagram now for this non-abelian case. And in the way that we know from, as you may have seen in the ordinary abelian story, to Fried and others, the abelian differential cohomology is meant to classify the gauge fields, like RR fields that are abelian. We generalize this here to this non-abelian case, which also includes these 5D supergravity and 11D supergravity cases. And then, since our differential form data here actually encodes the equations of motions, this is important, right? This is just a flux quantization. The equations of motions are imposed here. They only concern this piece. So this is actually the on-field higher gauge field configuration, and as such is the phase space. And next time we consider the topological observables on this phase space and quantize them. All right, thanks.